The work of the sea focuses on the coastline, the break between land and sea surface. Because of the sea's constant activity, the coastline is gradually but continually changing. The coastal features resulting from the work of the sea are dependent upon two factors: tides and the action of waves. Tides are caused by the gravitational pull of the moon and the sun on the Earth's surface. This is the same beach at high tide, when the sea is at its maximum height, and at low tide, when it is at its minimum. Low tide is also known as low water, and high tide is also known as high water. The area of the coastline which is covered by sea for only part of the day, between high and low tide, is known as the intertidal zone. The area influenced by the tides depends on the steepness of the coastline. A very shallow angle will allow the tides to cover a wide area. As we alter the steepness of the coastline, see how the area of the intertidal zone decreases. Waves are created by the friction caused by wind on the water surface. In general, the stronger the wind, the more fierce the wave action. Large, destructive waves which remove beach material are usually present during storm conditions. Other waves help to build the beach up by accumulating material and are called constructive waves. Under calmer conditions, when there is less wind, the waves are smaller and have less effect upon the beach. We can now consider how the action of tides and waves influences the various sections of a coast. The area of the coast permanently covered by water is called the offshore zone. The intertidal zone, or the zone between low and high water, is the area most affected by the action of waves and tides. This zone can be made up of sand, a mixture of sand and pebbles, or rocks. Sand is made up of grains of different types, but all of about the same size. It usually contains some white or colorless grains of quartz, fragments of local rock types, and fragments of shells. In some beach areas, particles larger than sand may also be present. These consist of grit, small and large pebbles and cobbles, and they all have the common feature of a rounded appearance. If the beach deposits are higher than high water, then the area they cover is called the backshore. Backshore deposits can only be formed during periods of intense wave activity, when material can be thrown above high water. For this reason, a beach on the backshore is commonly called a storm beach. Material making up the storm beach is usually much larger than the material found on the beach in the intertidal zone. Look at this typical beach, with sand in the intertidal area, but a conspicuous ridge of larger pebbles and cobbles making up the storm beach. Coastlines take various forms. They may end at the storm beach. There may be a cliff line with a beach exposed at low tide. Or the coastline may consist simply of a cliff line with no beach. We can now consider where beach material comes from, what happens to it while it is on the beach, and where it ends up. We can look at this as a system of inputs, throughputs, and outputs. In this part of the program, we will look at inputs, the sources of beach material. Material may enter the coastal system from inland by way of rivers. However, the most important input into the coastal system is the breaking down of the cliffs or land behind the beach. This breaking down process is known as weathering. Nearly all cliff lines are made of rock types which have some sort of weakness within them. It is very rare to find a perfectly uniform rock type. The processes of erosion attack these weaknesses to break down the cliff. Weaknesses in cliffs include bedding planes, lines which separate layers of rock, each layer being called a bed. Each bed was laid down separately when the rock was first formed, millions of years ago. Rocks of this type are called sedimentary rocks. Most rock types are bedded. Bedding planes can often be seen in the rock as separate bands of different color or thickness. Cracks running down the rock, across the bedding, are also lines of weakness. These cracks are called joints and were formed by the weight of the overlying rock pressing down on older, lower layers. Some cracks are formed by movement in different areas of rock. These are called faults and can be seen as an interruption in the regular line of bedding. All three types provide lines of weakness for processes of erosion. There are a number of different processes that operate on the coastline. When it rains, the cracks in the rocks sometimes fill up with water. In time, the water should evaporate or drain away, but if the temperature drops so that the water freezes, an ice wedge will form in the crack. When water freezes, it expands, and so the wedge will push the rock outward. The crack will expand and deepen so that when the ice melts, it is much bigger than before. This process can continue over and over again until the original rock is broken into fragments. This process is called freeze-thaw. In Britain, the correct temperature for freeze-thaw occurs in winter. Areas that are permanently frozen, such as the poles, and areas where temperatures never reach as low as freezing, do not experience freeze-thaw. Remember, for freeze-thaw to operate, there has to be a cracked rock, rainfall, and a fall and rise in temperature from above to below freezing. Cliff faces high above sea level are subject to the process of freeze-thaw. The material is loosened so that it may come down the cliff face in the form of a cliff fall and add angular material to the beach. The force of waves smashing into the base of a cliff squeezes seawater into cracks, which is later released when the wave retreats. The constant pounding of the waves and changes in pressure on the cliff face weakens it, and so fragments break off. The effect is increased due to the air trapped in the water exploding out of the cracks as the wave retreats. This process of wave action on the cliff is known as hydraulic action. The effect of hydraulic action is increased when the waves breaking against the cliffs are carrying fragments of rock such as small pebbles. Here we can see pebbles which the waves have lifted from the beach and thrown onto the promenade. These are used as tools when thrown against a cliff face, causing an increase in the rate or amount of erosion. As the fragments hit the cliff, they are broken into smaller pieces and become more rounded. The sea's use of rocks as erosive tools is known as corrasion. Corrasion is one reason for the rounded appearance of beach material. Seawater contains salt and many other chemicals. Here we can see salt crystals in dried up rock pools. Chemicals in the seawater can rot the rock at the cliff base and weaken it. The action of chemicals on rock is known as corrosion. Corrosion is the only process which cannot be seen actively taking place, but it is, nevertheless, very important. The erosive processes of hydraulic action, corrasion and corrosion act mainly on the base of the cliff, causing an indentation known as an undercut or wave-cut notch. Rock fragments, as well as being thrown against the cliff, are also thrown against each other. The effect of fragments hitting each other with force causes the same rounding down as the process of corrasion. This process is called attrition. Attrition can take place constantly, so it is this which is mainly responsible for beach fragments becoming rounder and smaller in size the longer they are on the beach. We have now considered the main processes of coastal erosion and weathering. Freeze-thaw, hydraulic action, corrasion and corrosion are all inputs into the coastal system, whereas attrition is an erosional process taking place on material which has already entered the system. A third input into the coastal system is material being brought up from the seabed offshore. This input is less important than the first two we have considered. We can now consider throughputs, the means by which material already on the beach is moved along it. This may mean movement up and down the beach in one place due to the swash and backwash of waves, or it can mean movement of material along the coastline. Let's concentrate on the movement of material along the coastline, using a plan view of a beach. Beach material is moved by the energy of waves. For movement along the beach, the waves must approach the beach obliquely, or at an angle. This angle is called the angle of wave incidence. Remember that the direction of waves depends upon the direction of the prevailing wind. For this demonstration, let's focus our attention on one solitary pebble on the beach and see what path it takes. As the wave crest reaches the beach and break, they transport material up the beach in the swash, in the same direction as they have been travelling. As the wave retreats, the material can stay at the upper point or be pulled back down the beach in the backwash. This time, the pebble moves straight off the beach along the steepest path. The next wave treats the pebble in the same way until eventually the pebble has migrated along the beach by many short stages, its path of transport making a saw-tooth pattern. The overall movement of the pebble is along the beach. This process is called longshore drift. All material on the beach is subject to longshore drift. Smaller particles are usually lighter and so can be moved more easily. Larger and heavier fragments are moved only when the waves have lots of energy. All this time, the erosional processes of corrosion and attrition continue, so that in time the particles get smaller and more rounded. This process is important in building up depositional coastal features. We will look in more detail at one of these features, landforms known as spits, in another program. Although material may be moved along the beach, the volume or amount of material making up the beach as a whole stays the same. This is because as new material is entering the coastal system, other material is being removed. This removal of material can be considered as the output from our coastal system. Beach material can be moved in two directions, offshore and inland. Material is removed from the beach in different ways, depending upon the direction in which it is moved. Firstly, movement of beach material out to sea. Strong waves may pull beach material off the beach with a fierce backwash. The material can stay part of the beach in the offshore zone, or it may be pulled further offshore by rip currents, which are common just offshore of many British beaches and can be highly dangerous. Material removed in this way becomes part of the seabed, although in some instances marine processes can raise it back onto the beach again. Movement of material inland is the result of the work of onshore wind. Wind is not as good a transporter of material as water and will only manage to pick up and transport the smallest particles, normally the finest sand on the beach. The wind lifts the sand and carries it landwards where it is deposited to form sand dunes. program, we will look at how the various coastal processes we have studied act on the coastline to produce different types of landform. We will look at erosional landforms, which are formed by the breaking down of the coastline, and depositional landforms, which are formed by the movement and depositing of material. In the first part of the program, we will look at erosional landforms. Landforms created by coastal erosion depend upon two factors: the geology or character of the rocks and the way in which the sea acts on the rocks. Let's look first at how geology controls the shape of the cliff line. Many cliffs are made up of layered sequences of rocks. The layers are called beds, and the planes separating each bed are called bedding planes. The bedding planes act as lines of weakness and are prone to erosion. When the cliffs at the back of a beach are made up of bedding planes which slope seawards, they are usually unstable. This is because any weakness between the bedding planes acts as a slippage plane, allowing pieces of the rock to slip down the cliff under the influence of gravity. This often happens after the cliff has been weakened by weathering. Here we can see that these rocks have bedding planes tilted towards the sea, and the cliff is very unstable. Large pieces of rock have slipped down the cliff onto the beach. Cliffs which have a bedding plane which is tilted inland are usually more stable. This is because any slippage along the bedding planes would have to be in an inland direction. This is unlikely to occur unless the cliff is being eroded from behind. Cliffs with horizontal bedding are also stable because the planes separating each bed do not allow slippage in either direction. For some cliff lines, bedding is not the most important factor governing the way in which the cliff is eroded. In cliff lines which are made up of soft rocks, such as sands and clays, the cliff may collapse along a plane which cuts across bedding. This plane is normally arc-shaped. The rock will rotate as it falls so that the toe of the slipped block points outwards and the cliff top points backwards. Because of this, the process is called rotational slip. So the types of rock which make up a cliff are important factors in the way in which the cliff is eroded. Two different rock types are found in these cliffs. The darker coloured beds are made up of shale, a soft black rock which splits easily along many cracks. The rock is very soft compared to the other rock types, and due to corrosion quickly breaks up into minute fragments to form part of the sandy beach. The lighter rock is siltstone, which is much harder and forms thicker beds. When these rocks are eroded, they land on the beach as larger fragments. They take a long time to erode further and form cobbles and large pebbles. Because the harder siltstone is eroded more slowly than the softer shale, it sticks out or protrudes from the rock face. We have now considered how geology affects processes of erosion on certain cliff lines, resulting in distinctive coastal features. We can now go on to look at how the geology over a larger area affects the overall shape of the coastline. In some regions, alternate hard and soft bands of rock run at right angles to the coastline. Here we are looking down at a plan of a section of such a coastline which may be several miles long. As the softer rock is eroded more quickly than the hard, this area of the coastline retreats more rapidly than the hard rock areas. This results in the formation of a series of headlands and bays. A series of headlands and bays formed in this way is known as a discordant or Atlantic coastline. If hard and soft rock bands are parallel to the coast, as in this plan, different coastal features are formed. Let's look at a section of the Dorset coast which has this type of geology. These cliffs are made of limestone, which is a hard, resistant rock. If we look behind the rock, we can see that in some places the sea has broken through. Once the sea has eroded the limestone and reached softer, less resistant rock, it begins to remove this soft material from behind the limestone cliff line. As the sea continues to erode the limestone cliffs, large arches may form. Remember, the area between the arch and the present beach was once land, but because the rocks were soft, they eroded more quickly once the limestone cliffs were breached. Erosion of the limestone continues until all that is left of the original cliff line are some offshore stumps of rock. The geology of this area and its effect on rates of erosion can be used to explain how this cove was formed. We can see that once the resistant limestone cliffs have been breached, the sea rapidly erodes the soft clays behind. This continues until the sea reaches more resistant rocks, in this case chalk, which forms the back of the cove. If we look at the sides of the cove, we can see the outermost resistant limestone, behind that the softer clay, and at the back of the cove the resistant chalk, which forms a cliff. The name given to this sort of coastline is either concordant or Pacific type. Headlands, although resistant, do not stay forever. They can be eroded in conventional ways by undercutting or by another process requiring the presence of a particular weakness in the headland. Headlands of all sorts can be eroded, those of discordant and concordant types. Take this, a typical headland, from side view. The sea picks out a weakness in the rock, such as this fault. As time progresses, the sea preferentially erodes the weaker fault line to produce a cave. At this time, the sea is probably forming a cave on the other side of the headland in line with the one on this side. Erosion continues until the two caves join to form a clear passage through the headland. This feature is called an arch. The sea undercuts the base of the cliff around the arch, so material is loosened and the arch becomes wider and higher. The ceiling of the rock above the arch becomes thinner. Processes of corrosion and hydraulic action are important in this sequence. Once material is loosened from the arch roof, it falls under the influence of gravity, and it is then eroded constantly by the sea lapping at the arch's base. It is soon removed. Eventually, the arch collapses in spectacular form, leaving a new cliff line and a separate tower of rock called a stack. Undercutting continues, and the stack reduces in width and height until it is so small it is called a stump. Eventually, the stump disappears to form part of a widening rocky platform left after headland erosion. This platform is the only visible result of where headland erosion has occurred on some coastlines. It is called a wave-cut platform. Here is the whole sequence again, one stage at a time. This headland shows stages in the sequence illustrated earlier by computer graphics. We shall now look at depositional landforms, which are also distinctive coastal features. Beaches are the main landform resulting from depositional processes. They serve as transport media, but can also be a depositional feature in their own right. The most common beach is the bayhead beach, formed on discordant coastlines as an accumulation of sandy material at the innermost part of the bay. Sand on the bayhead beach may not move along the coast at all. Along more open coastlines, longshore drift moves material along the beach. If there is a break in the cliff line, a feature known as a land spit may form. Material moved along the beach by longshore drift builds up on the edge of the headland. Gradually, the amount of material increases and the deposited sediment builds up into the bay, forming a land spit. As the sediment builds up, various environments are created, and at the head of the spit, a sand dune system develops. At low tide, wind dries the sand and blows it into high mounds, which may be above high tide mark. In this way, new land is beginning to form. The sand dunes build up in stages. Looking at the sand dune system, we will see that older dunes are further inland than new dunes and have different characteristics. Sand dunes are formed above high water mark, when sand blows inland from the beach and becomes trapped by beach debris such as seaweed or driftwood. Small mounds known as embryo dunes are built up. Marram grass is a plant which is capable of surviving in this harsh, salty environment. Once the grass starts to grow on the embryo dune, it traps more sand and its roots stabilize the dunes. This enables the dunes to become much larger. These larger dunes are called mobile dunes. They are covered in marram grass, but few other plants are capable of surviving. Moving inland, the amount and variety of plants growing on the dunes increases. These dunes are known as semi-fixed dunes. The plant roots help to bind the sandy soil so that the dunes are more stable and less salty. As they become older, the amount of plant cover increases still further. The dunes are more stable and are known as fixed dunes. Towards the landward side of the dune system, the older sand dunes form dune slacks, which may contain ponds and support trees and shrubs. The area behind the spit is now protected from the strong coastal wave and wind action and develops into a lagoon, bog, salt marsh or intertidal mudflat. Water covers much of the surface of the earth. It forms oceans, lakes, rivers, and is also present in the air as clouds or vapor. Water is continually moving between these different environments. This movement can be described as a never-ending cycle, which is known as the hydrological cycle. The hydrological cycle consists of many stages. Water is continually passing through these stages. In the first section of this program, we will trace the path of water through the cycle beginning at the open sea. Water at the sea's surface is warmed by heat from the sun. Some of this water evaporates, turning from a liquid into a gas called water vapor. This process is called evaporation. The water vapor is dispersed through the air, which may be moved by winds. Onshore winds transport air landwards, carrying the evaporated water or water vapor with it. This process is called transportation. The air and water vapor are carried over the coast and further inland. If the landscape is hilly or mountainous, then the air is forced to rise. As the air rises, it cools and can hold less and less water vapor, which changes into small water droplets and forms clouds. This process of water vapor changing from gas to liquid is known as condensation. When temperatures are low at ground level and the air contains much water vapor, condensation may form fog or mist. Water droplets in the clouds may combine with others to form larger droplets, which then fall onto the ground as rain, hail, or snow. This is known as precipitation. Once the precipitation reaches the ground, it can take a number of courses. If we look at the typical cross-section through the ground, we can see that it is made up of soil covering solid rock. We refer to the solid rock as bedrock. If the ground is dry, then precipitation will soak in. The ground acts as a sponge, allowing the water to infiltrate into the soil and bedrock. This is known as infiltration. Infiltrated water, known as groundwater, may stay for some time in one place in the ground. However, usually the groundwater will move from high to low ground under the influence of gravity. Once groundwater starts to move, it is known as through flow. Through flow may take place through both the soil and the bedrock. Here we can see through flow taking place as water flows out of an exposed section of soil. Sometimes the soil becomes so wet that it cannot hold any more water. It is then said to be saturated. If it continues to rain, water cannot infiltrate into the saturated soil, and so it stays at the surface and may flow over the ground as surface runoff. Sometimes surface runoff takes place when the soil is not saturated. This happens during very heavy precipitation or when the soil type does not allow water to soak in. Once water has reached the ground by precipitation, it may flow back into the sea via a number of different routes. We will now look in more detail at what happens to the water between reaching the ground surface and entering the sea. Our landscape is not flat, but irregular. The irregularities can be small, giving gently undulating land, or they can be great, giving hilly or mountainous land. Whichever, we can divide our landscape into steep or shallow slopes, which commonly have at their base moving water at the surface in the form of a river. Water moving as through flow or surface runoff may drain into bogs and marshes. These give rise to springs, which drain into streams, then rivers. Water may also enter the rivers directly as through flow or surface runoff. In summary, water may enter a river by several means: by precipitation directly into the river, or by surface runoff and through flow either directly or via bogs and marshes. The stream or river acts as the main channel for quick exit of water away from the source area towards the sea. We can divide our landscape into areas which act as basins or funnels for drainage. The area of slopes draining into a river is known as the drainage basin. Different drainage basins drain into different rivers. Rivers quickly remove water from the drainage basin as they flow towards the sea. Now let's look more closely at the river channel itself. Rivers are channels which have water flowing in one direction. The base of the river is called the bed and can be made of bedrock or covered by loose rocky material called sediment. The river sides are called the banks, and the top of the water is called the water surface. These parts of the river can easily be identified. During periods of little precipitation, the water entering the river as runoff and through flow decreases. The water surface lowers to form a shallow river. A river in this state is termed below bank full, as the water surface is below the top of the banks. When the water surface is level with the top of the banks, the river is said to be bank full. This occurs during periods of heavy precipitation when there is more water entering the river via through flow and surface runoff. If the water surface continues to rise above the level of the banks, the excess water spills out of the channel as floodwater. We have already seen that the loose material may cover the bed of a river. A general term for this material is river sediment. In the second part of our program, we will see how sediment enters the river. There are two main sources of river sediment. Material may enter the river from surrounding slopes or from the river bed and banks. Material enters the river from surrounding slopes by moving downhill in a number of ways. Remember, there are two sorts of slope material, soil and bedrock. Because soil is made of loose fragments, it can be washed down the slope by surface runoff. Soil can also slip down the slope in larger amounts by a process known as soil creep. Evidence of soil creep can be seen on steep slopes by the formation of turf rolls. Bedrock cannot move in these ways, as it is solid. For any movement, the bedrock must first be broken up into fragments. The main process which causes this is freeze-thaw, but this can only work where the bedrock is visible above the surface. This sequence shows the freeze-thaw process in action. Freeze-thaw can be so effective at loosening the surface layers of bedrock that both soil and loosened bedrock can slip down the slope in large amounts. This may result in the formation of rills and gullies. In this way, a great deal of material can enter the river very quickly. Any soil which reaches the river is quickly washed away, as the particles are normally very small. Larger rock fragments, released by freeze-thaw, sink to the bottom as they are heavy and form part of the river sediment. These fragments are large and angular, but soon become smooth and rounded. However, most of the sediment in the river comes from the bed and banks, as the river actively wears or erodes them away. In this part of the program, we will look at how material is eroded from the river bed and banks and then transported downstream. Once material is in the river channel, it can be moved downstream by the flow of water. River sediment can be divided into a number of types. Each type is called a lode. The largest and heaviest material is transported by rolling along the bed. As it never loses contact with the bed, it is called bed load. Smaller particles are moved by rolling and bouncing, as they are lighter than the bed load, but not light enough to be carried above the bed for long distances. Particles which bounce are said to saltate, and so this is called the saltation load. The smallest and lightest particles may be carried in the water above the bed surface. These particles are suspended in the water and are so called the suspension load. Finally, some material is soluble in water and is carried downstream dissolved in the water. This is called the solution load and obviously cannot be seen. We now have seen how river sediment is transported downstream in different ways depending upon the size of the sediment particles. But this is not the only factor affecting the way in which the sediment moves. For any movement of sediment, moving water is necessary. We can call the speed of water flow velocity. As river velocity increases, the amount of material it can transport also increases. Under conditions of very high velocity, the size of sediment particles is less important. This sequence, filmed under laboratory conditions, shows how one type of sediment, in this case sand, is affected by different water velocities. When the water is moving very slowly, the sand is not moved. Water with a slightly higher velocity causes the particles to roll. Some particles may be seen to saltate. As the velocity increases, ripples start to form in the sand. As the sand is transported, the ripples move in the same direction. At very high velocities, the ripples disappear and the bed of the river becomes flat again. However, we can now see the sediment is rolling and saltating and is also being carried in suspension. In real rivers, the velocity fluctuates over time and the river sediment is made up of particles of different sizes. So both factors of river velocity and particle size are important. As river sediment is transported downstream, it may be thrown against the banks or against areas of bedrock on the river bed. The river uses the rock fragments it is transporting as tools, which are able to erode the river banks and bed to provide more fragments for the river to transport. This process is known as corrasion. At the same time, the particles in the river may collide with each other and shatter or have their corners knocked off. This process is called attrition. Both corrasion and attrition are responsible for particles becoming rounded as they are transported downstream. have already studied river processes in an earlier program. Now let's turn our attention to the landforms produced by these processes. If a section is taken along the length of a river from source to mouth and plotted as a graph, it will normally produce a profile such as this, called a long profile of the river. The steepness or gradient of the river becomes less towards the mouth. This change in gradient results in the development of a variety of landforms at different stages down the river. The main action of the river on the landscape is downward cutting, called vertical erosion. Looking at the development of the long profile over a long period of time would show it becoming shallower and smoother. Eventually, the profile is nearly horizontal and perfectly smooth. However, there are times when the long profile cannot form a perfectly smooth line. Bands of harder rock cutting across the river form resistant ridges, which the river has to cut through or flow over. Sometimes the more resistant bands are flatter, causing the formation of a pool called a plunge pool, and undercutting, where the river flows across hard, then soft rock types. Faults have the same effect, sometimes bringing softer rock into contact with harder rock. Now we will look at how the characteristics of the river change from source to mouth, beginning with the upper course. The highest section of the river is called the upper course or youthful stage. Rivers originate from upland lakes, bogs, or springs. At this early stage, the river is small, but because of the steep gradient, it is fast flowing. The river sediment is large and angular, as it has not yet travelled far. Attrition will continue to work on the sediment as it travels downstream. The river is shallow enough and the bed load large enough to protrude through the water surface, giving an irregular, rocky appearance. This is a section across the river and valley sides called a cross profile. It is taken at right angles to the long profile. This shows a river unable to move sideways as the valley sides come right down to the riverside. There is no true valley floor. The river concentrates solely on vertical erosion. In 3 dimensions, the river takes an irregular course around the hillsides. Each hillside which obstructs the course of the river is called a spur, and as the spurs overlap, they are called interlocking spurs. Interlocking spurs are a characteristic of upland rivers. River sediment will be transported along the river during periods of high river flow called spate. The size of the bed load is so large that ordinary river speeds will not move it. In other parts of the river, the bed load is seen as a series of ridges and troughs called riffles and pools. The riffles migrate downstream over a period of time. Many upper course rivers have extensive gorges where the river has cut down. In softer rock, down cutting may cause the river bed to form potholes. Some small rocks become trapped in the river bedrock. Water flowing over these stones is disturbed and begins to swirl around. This swirling action moves the stones around continuously, using them as a tool to carve a wider and deeper hole. This corrosive action causes the pothole to become smooth and rounded. Eventually, the potholes will become so wide and deep that they will link up to form a new lower river level. As the river reaches the middle section of the long profile, it develops into the middle course with its own characteristics. In the middle course, the river gradient is much shallower than in the upper course. This allows the river to erode sideways as well as downwards. Sideways erosion is known as lateral erosion. This plan of an upland stream has an irregular course with interlocking spurs. The water flow in the river is in this direction. Maximum erosion takes place at these points, so the river will wear away the spurs as the course of the river moves down the valley. Eventually, the river has formed a parallel-sided valley and is free to migrate across the valley floor. Bends within the river are called meanders, and they can develop over the area of the floor of the valley. For this reason, the valley floor is called a meander belt. Meanders do not only form just small bends in the river, but can also develop large loops. Let us look at a meander formation in more detail and see how they develop. Take this small bend in the river with river flow in this direction. If we plot the line of fastest flow within the river, we can see that it swings from side to side, thrown about by the irregular path of the river. It follows that maximum erosion will be at these points. This causes the course of the river to change. The swinging to and fro of the fastest current causes the meanders to grow sideways. As it does, so both ends of the meander begin to come closer together, until eventually they join, leaving the meander abandoned. River material will quickly fill the gaps at these points, separating the old meander from the new course. The old meander is now called an oxbow lake. A cross-section through the meandering river shows an asymmetrical shape, with the deepest part on the river on the outside bank where the flow is fastest. Here the bank is undercut by the river, releasing material into it. Therefore, this bank is named the cut bank. The opposite side of the river looks very different. There is no steep bank at all, but an area of sediment made up of all sizes, which rises gently from the water's edge. This is called the point bar. The point bar develops in the shallowest water, where the river flows most slowly. The sediment in the river is carried up and deposited onto the point bar during times of high flow. The lower course develops when the river has nearly reached base level. Here, the gradient is very shallow, and the amount of water in the river is at its greatest. The river can therefore be very large. The lower course has similar characteristics to the middle course, but as we follow the river valley downward, the valley sides become wider and wider as a result of meandering. Eventually, the river will cut a valley floor that is so wide that it can only meander over part of it at any one time. The meander belt and the flat valley floor are different sizes. Parts of the meander belt, not now used by the river, stay unaffected by erosive activity. However, during storms, the river has too much water to hold as bank full, so it will flood out onto the valley floor. We call the valley floor a floodplain. In this case, the floodplain has a meander belt running across part of it. Floodplain sediment is very fine, as it is the suspended load which gets carried out of the channel. Only very rarely does the larger bed load find itself on the floodplain. We can see floodplain sediment in the cut bank of some meanders. It is fine, brown and thinly layered, with each layer corresponding to one flood event. Once eroded by the meander, the floodplain material will once again become part of the suspended load of the river. A cross-section through a lower stage valley shows a wide, flat valley floor with a river course running through it. The river is kept in by naturally formed ridges of sediment called levees. How do they form? When the river floods, it carries material out of the channel and onto the floodplain. As the velocity of the water decreases, the sediment it carries is dumped. Most of the material is dumped above the bank of the river as the water flow begins to slow down. Rivers eventually reach the sea. At this point, the flow of the river is stopped by the seawater, and any sediment the river has carried is deposited at the river mouth. By this time, the sediment can be very small indeed.
If the sea is powerful and quickly erodes or transports the sediment away, then the river mouth is kept clear. In Britain, the sea is powerful enough to transport most river material entering the sea. Glaciation is the term used to describe the action of ice on the landscape. This is a small glacier. At this point, it is about 400 meters wide. In Britain, snow may fall and cover the ground during winter. As our climate is mild or temperate, it usually melts within a few days or weeks. In colder climates, such as the polar regions and high mountains, where air and ground temperatures are low all the year round, the snow will not melt, but will persist from one winter to the next. This build-up of snow results in the formation of ice. In temperate climates, snowfall may create a thick snow cover. But even thick snow will melt during the summer, when the weather is warmer. In colder climates, the summer temperatures are not high enough to melt all the snow, and some may remain from one winter to the next. This will be covered with new snowfall. Over a number of seasons, a thick snow cover accumulates. The weight of the overlying snow compresses the older layers underneath so that they become thinner. When fresh snowfall compresses older layers near the surface, the compacted snow becomes dense, like a snowball. Lightly compacted snow, which is at least 1 year old, is called névé. As the overlying weight of snow increases, the névé compacts so that the individual snowflakes and ice crystals melt under pressure, only to refreeze to form ice. This much denser and harder substance is known as white ice. Older ice is blue in color, as air which was trapped in the snow is squeezed out. This is known as blue ice. At the very base of the ice, the layers are at their hardest and thinnest and are in contact with the ground surface. Pockets of air may remain locked in the ice. There are sometimes darker streaks of rock debris between layers. There are also bands or striations in the ice which correspond to annual snowfall and melt. In summary, as the ice becomes older, the layers become thinner and harder. Older ice is blue in color. Today, areas of ice are found in two distinct regions, over the polar regions and over high mountains. This is because of the low temperature at the poles and at the high altitudes. In polar regions, ice builds up in large areas to form ice sheets. The ice sheets cover all of the landscape and can be very thick. The edges may spread out from the main ice center. In some areas, the ice flows into the sea, forming ice shelves. Large pieces of ice break off and form icebergs. In warmer climates, large ice sheets do not form, and glaciation is not so severe. However, in highland areas such as the Alps, ice tends to build up in separate valleys as cirque or corrie glaciers. Ice within the glacier moves downhill under the influence of gravity. Cirque or corrie glaciers may join to form larger valley glaciers, or spread out at low altitudes to form a different sort of ice sheet called a Piedmont glacier. Ice on any slope will flow downhill. Generally, this movement may occur in three ways, depending on the depth of the ice. Upper layers of ice respond to movement by snapping or cracking to form crevasses. This is especially true when ice is moving over a humpy or irregular ground surface. The top layers crack or pull apart at the point of most tension. Crevasses account for only small amounts of ice movement. The whole glacier can move by slippage over the ground. Because of its weight, there is a great deal of friction between the ice and the ground surface. However, water under the ice acts as a lubricant, allowing the glacier to move. Here we can see water coming out from the underside of the glacier. Movement may occur between the bands or striations in the ice. Ice can also flow by bending rather than cracking. In summary, ice may move downhill in three main ways: cracking at the surface to form crevasses, slippage along the ground surface, and internal movement between ice layers. Now let's concentrate upon the source of a valley glacier, which is called a corrie or cirque. This is where erosion starts. This shows a long profile of a typical valley in an area about to be glaciated. As snow persists, the ice layer thickens and the process of erosion begins. As ice builds up, it moves down the valley. As it flows downhill, ice near the top of the slope becomes thinner and the ice further down becomes thicker. The profile gets deeper as ice wears away the ground surface or bedrock as it moves over it. Later, we will see that to do this effectively, the glacier uses rocks as tools. The thicker ice has a greater weight and wears away the underlying rock. The wearing away of rock is called erosion. As the glacier ice erodes downwards, a hollow is formed in this part of the profile. Ice has to undergo rotational slip to move out of this area. Rotational slip is the term used to describe the curving movement of ice as it leaves the hollow. This hollow is now called a corrie, cum, or cirque. At this point, the ice is in fact moving uphill due to pressure from behind. Separating the corrie from the rest of the valley is the rock lip or sill. As the ice moves over this, crevasses form. At the back of the corrie is a steep rock face called the back wall. At times, ice movement down the valley is so fast that the ice is pulled away from the back wall and a gap opens up. This gap is called a bergschrund. This feature is similar to a large crevasse, but in this instance, the crevasse exposes the rock of the back wall to weathering, mainly freeze-thaw. Weathering weakens the rock, which eventually breaks up and falls as boulders to the base of the bergschrund. The boulders, which are angular and of various sizes, are swept under the base of the ice as the glacier rotates. These rock fragments are used by the ice as tools which increase the rate of downward erosion. The effect of using tools as an erosive agent is called abrasion. The rock fragments act in a similar way to grains of sand on sandpaper when it is rubbed against wood. The paper itself would not be effective without the sand grains. The lower or basal layers of the glacier are dirty due to the rocks in the ice. The material in the ice is called moraine. Freeze-thaw also acts on the cliffs along the valley sides to release rocks which fall onto the surface of the glacier. As the ice melts, refreezes and moves forward, the rocks may sink some way into the ice. As the glacier, armed with its moraine tools, moves over the ground, it carves out more rocks, which are picked up by the ice. When ice moves over an undulating ground surface, it may break fragments from the bedrock. This is a typical undulation of ground surface. As the ice travels, it rides up the front or upflow side of the undulation, smoothing it off. On the downflow side, the glacier pulls off fragments as it passes. These fragments can be removed in two ways: by friction between the glacier ice and ground surface, or ice flowing into cracks and joints in the bedrock and including them into the base of the glacier, which is then called plucking. This results in a feature with a long, smooth upslope and a short, steep downslope. This feature is called a roche-moutonne. Rocks are released into the glacier by freeze-thaw action on the bergschrund and valley sides and plucking under the basal portion of the glacier. Eventually, as temperature increases slowly, there is more ice melt or ablation than ice formation. The ice thins and the rotational slip mechanism stops. Bergschrund activity also stops, and the glacier fragments at its thinnest point on the rock lip. As the rest of the ice melts, the rock lip holds back the water to form a lake. A lake of this sort is called a corrie lake or tarn. Ice underneath the upper portions of these glaciers is forming corries today. They will not become visible until and unless the ice retreats completely to reveal them. This is a typical corrie in North Wales, showing many features of glacial erosion. Features found in corries like this are discussed in another programme. We have already looked at the formation of ice and the ways in which it can erode the landscape, mainly through corrie formation. We will now concentrate on glacial deposition and then on glacial landforms in Britain as they are seen today. Firstly, let's revise our understanding of different types of glacier. A broad division can be made between ice sheets at the poles and isolated glaciers elsewhere. The individual glaciers begin as corrie glaciers and then flow together to become larger valley glaciers. These may then flow out onto flattened land as Piedmont glaciers. However, some valley glaciers never change into Piedmont glaciers but remain in their valleys. In the first part of the programme, we will look at the ways in which glaciers deposit material. The front end of a valley glacier is called the snout. As this moves forward, it strips away soil and loose rock, pushing it forward in front of the snout. Eventually, the snout will stop moving forward. That is, when the rate of ice melt is greater than the rate of ice formation. As it retreats, the loose material is left as a ridge. Material transported and deposited by ice in this way is called moraine. This particular type of moraine is called an end moraine, as it has been deposited at the end of the glacier. Moraine is typically a mixture of angular rock fragments of all sizes. The finer material is often deposited as a clay, so moraine is sometimes also known as boulder clay. Moraine also comes from under the ice. As the glacier passes over crags of rock, it picks up fragments by plucking, so the lower parts of the ice become loaded with rock fragments of all sizes. When the glacier retreats through ice melt, the area it previously covered is left with a cover of moraine, which looks hummocky and is called ground moraine. When ice retreats, it leaves an end moraine. However, it's common for the glacier to retreat in summer when it is warmer, but advance slightly in winter. This may give a series of end moraines, which can be called recessional moraines, as the snout is in general receding. As the glacier retreats and the ice melts, water flows out of the snout. In winter, this is just a trickle, but in summer, the meltwater can form a torrent. The water carries large amounts of moraine released from the ice. Sometimes the meltwater leaving the snout will be trapped by an end moraine. Because moraine stops the flow of water, a lake begins to form. This lake is called a proglacial lake. As the flow of water is stopped, the fragments it carries are dropped to form lake deposits. These are formed partly by ice and partly by water, and so are called fluvio-glacial deposits, also known as outwash deposits. These look very different to the moraine. They form horizontal layers called beds, and because of the processes of attrition and corrosion taking place in the water, these fragments are smaller and much more rounded. Eventually, the water will break through the moraine dam and deposition will stop as the lake drains. In other areas of the valley, the glacier is not depositing, but eroding by cutting deep into the floor of the valley. This is termed over-deepening. A shallow lake called a ribbon lake may later form in the over-deepened part of the valley. Valley glaciers are sometimes joined by smaller tributary glaciers. As more small glaciers join, the main glacier becomes wider and deeper to accommodate the extra ice. This means that the main valley glacier erodes more deeply than the tributary glaciers. If the ice is removed from the area, we can see that the tributary glacier is hanging above the floor of the valley glacier, and it is therefore called a hanging valley. We can now look at the effect of glaciation on the landscape by looking at the scenery in North Wales, which was once glaciated. We will look first at where the glaciers began, in the corrie. Corries like this occur over much of Britain that was once glaciated, mainly in Wales, the Lake District, in northern England and Scotland. More than one corrie eroding into the landscape may result in the formation of a steep point at the back of the basin, called a pyramidal peak. The sides of the corries start from this peak. Over-steepening by the ice forms narrow, knife-edged ridges called arêtes. The original position of the berggrund is marked by a steep wall at the back of the corrie, called a back wall. Material from the back wall entered the glacier by freeze-thaw. In many corries, the over-deepened part of the basin is filled by a lake called a tarn. The tarn is restrained by the rock lip, which sometimes has a covering of ground moraine, like this one. Where the bedrock is not covered with moraine, it may be smooth because of the action of the ice. Large pieces of moraine carried in the ice may have carved out indentations known as striations. A ridge of more resistant rock may protrude to give a roche moutonné. The upslope sides of the roche moutonné are usually smooth and may be covered in striations. Large areas of scree have developed on the sides of many corries since the end of glaciation. Freeze-thaw conditions have continued since the end of the Ice Age. As you look at this summary of features seen in and around a corrie, visualize how they look and recall how they were formed. After glaciation, the valleys are wide and U-shaped. The edges of hills, called spurs, which used to protrude into the valley, have been removed by glacial erosion to give truncated spurs. Rivers are free to meander across the wide valley floor. The over-deepened sections of the valley floor now have a shallow ribbon lake, while other areas are filled with moraine or fluvio-glacial deposits. The original junctions of tributary glaciers are now marked by hanging valleys, which have eroded back since the end of glaciation to give a gorge. However, in this case, the flat, wide floor of the tributary glacier can still be seen high up on the side of the main valley. If the ice in these glaciers in the Alps continues to melt, then landforms similar in kind to those seen in North Wales will be revealed.